We have here a wonderful simulation brought to us by PhET Interactive. It's part of the University of Colorado at Boulder, and they've provided a number of simulations that are available to people in not only chemistry, but also physics, biology, mathematics, and earth science. So if you are curious or studying some concept in any of those topics, it can't hurt to just Google PhET simulations and see if that concept has a simulation that they've made for it that you could then learn and see. It might be very helpful. I think these are great simulations. What this simulation will allow us to do is examine gas properties, particularly with the PV equals nRT formula in mind. Now, as you can see, we have a bicycle pump that will allow us to add gas particles to the container. And let's just assume that one full pump gives us 1 mole. And now we can change the temperature by adding heat or cooling it down. We can adjust the volume by changing the size of the container with that handle, giving the particles more or less room to kind of operate within. All of this, the temperature will be measured by the thermometer as we heat it, cool it, and see all the effects. And over here we have an air pressure gas gauge that will measure the pressure given all of the changes that we're putting in place. Now, what I'm going to do next is I'm going to add 1 mole of gas to the container. And my question to you is, what is your hypothesis about what effect adding a mole of gas particles to the container will have on the pressure? My hypothesis is that since P and N are on opposite sides of the equation in the PV equals nRT formula, that there's a direct relationship between them, and so increasing N will also increase pressure. So we're going to add 1 mole, and yes, we see that adding a mole of gas particles to the container does indeed increase the pressure. So what we've done is we've proved our hypothesis using the simulation, and notice that these gas particles are operating according to the kinetic molecular theory. They're moving in random straight line motion until they collide either with the walls of the container or another particle. And it's when they collide with the walls of the container that they cause pressure. Um, there's a key point here, though, that while the pressure is fluctuating, that's only because we have such a simple model with just such a few number of particles. In real life, given that a baggie full of air, like a sandwich bag full of air, has more air particles in it than all the grains of sand in all the beaches in the United States, there's so many colliding at every one time that the randomization that we see here isn't really valid. It's much more constant in real life because the sheer number of air particles that there are in nature. So just be aware of that, but also be aware that the particles in the middle that aren't hitting are kind of irrelevant. It's only when they hit. Now pay special attention to one thing. Pressure does not start until the first particle hits the wall. So watch again as I do this, and there, now the air pressure is being measured. So they did a great job of giving that little glimpse into why it's only the particles colliding with the walls that affects air pressure. So next what I'm going to do is we're going to hold the number of moles that we have here constant. We will hold we'll hold the volume constant, and R is a constant. Now let's change the temperature. What would happen to the particles if we added heat, if we raised the temperature? What's your hypothesis? What will happen to pressure if we raise the temperature? All right, so hopefully you have your hypothesis ready in your mind. I'll raise the temperature by a good amount so that you can see a decent effect on pressure. All right, so I'm increasing temperature. I've raised it by 100 degrees Kelvin. And notice the pressure has indeed gone up, which I hope was your hypothesis, given that pressure and temperature are on opposite sides of the equation. They should have a direct relationship to each other. And so increasing the temperature increases the pressure. So now what I'm going to do is we'll keep moles and R constant. We will keep temperature constant. What effect will it have if I change the volume? If we increase the volume, what effect will that have on pressure? What is your hypothesis? Well, as you can see, doing this has actually decreased the pressure. And the reason for that is because P and V are on the same side, so they have an inverse relationship. So increasing V means that P must decrease. Decreasing V should lead to P increasing. And you'll be able to see it because pressure is when they collide with the walls of the container. And if it's smaller, you can see that it's a lot quicker collisions because they're traveling. They'll hit a wall because it's a lot closer to themselves. Where if it's farther apart, they have to go a larger distance before they actually hit the wall again. So that's why pressure is decreased. So once again, the math checks out with reality. Okay, we can take a look at another set of the variables in PV equals nRT now. This time, let's keep the number of moles constant. R will be a constant. But let's keep pressure constant. Let's hold that constant, leaving only volume and temperature left as our two variables that we'll compare against each other. So what will happen to the volume if we increase the temperature? What is your hypothesis regarding an increase in temperature on the volume when everything else is held constant? Well, now let's see what happens. As we increase the temperature, the volume also increases. And again, volume and temperature, V and T, are on opposite sides of the equation, so that tells us there should be a direct relationship, and increasing one with everything else held constant should lead to the other also increasing. And so this is actually Charles's law, and he did an experiment in the early 1800s, early 1800s, I think, where he basically just took 5 different gases, put them in balloons, and then heated them up. And he saw that they all behaved exactly the same. They all went from the same original size at the first temperature to the same second size at the new temperature, which led them to understand that it didn't matter which chemical it was that was in gas form, they had all behaved the same, and that there was a relationship between volume and temperature that was a direct relationship. Now there's one more thing this simulation will allow us to show you, which is that we can open a lid and let air particles escape from the container to the outside. And you can see, or I can tell you that the pressures are about equal inside and outside because the gas particles will leave through random motion only. When there's a big difference between the interior pressure and the exterior pressure, there's a big rush. There's a statement, Mother Nature abhors a vacuum. It always tries to equalize imbalances. Like water is always level. It's never going to be like higher on one side than the other. In the same way, you'll have the same thing with pressure, where if there's an ability to equalize pressures, it will happen as quickly as possible. Which is why, like you always see in movies, whenever an airplane, which has a pressurized cabin, way up high, if the door goes off, all of a sudden people are getting sucked out the wind, out the door on the airplanes, because there would be an equalization of pressure, meaning all the gas particles inside the plane that's pressurized would rush out into the out exterior of the container, which is the plane. So, but in this case, please notice that when the molds leave the container, not only does pressure go down, which we would expect from our rule of thumb theory, but temperature also goes down. Notice it's a lot lower, and this may confuse you at first because N and T are on the same side. It might seem to violate our little rule of thumb that we've been operating under. But remember, the assumption that rule of thumb is based on is if everything else is held constant and we only look at two variables. And in this case, we have three variables at play: pressure, temperature, and moles. And so always keep your assumptions in mind when you're working with a model or you're working with some theory, just so you can be aware whenever those assumptions are violated, so that you know not to be so complacent in applying the rules of that theory. All right, I have one more thing to show you. Let's start fresh with 1 mole of gas particles. And you can see we're going to keep everything constant except, well, let's make it a little smaller so it's easier to see things. But now take a look here. We have the ability to add another type of particle. Oh, let's get this going so we can get the pressure as close as we can to 10 so things can be easy to work with. All right, good enough. All right, take a look at the pressure. Take a look here. We have a small red particle that we can use and add instead of the big blue one. So my question to you is, if we added 1 mole of this smaller red particle to the container, would the pressure double exactly? Would it be twice as much as you see now? Will it be less than twice as much as you see now? Or will the pressure be more than twice what you currently have inside that container? And I'll let you think about that and come up with your hypothesis. And then I want you to do one more hypothesis. What can you predict about the behavior of this red particle relative to the blue particle? This is a little more complicated. If you can get this right, you're pretty much ready to take my job, and we're not going to talk about that anymore. But give this one a thought. And when you're ready with your 2 hypotheses, let's test them by adding a full mole of this small red gas particle to the container. All right, here goes. And okay, we see 2 things. First of all, the gas pressure is exactly twice as much as it was before. And this shouldn't come as too big a surprise, because I'll point out to you that the formula says PV equals nRT. There's no mention of grams. There's no mention of the mass. There's no distinctions made between this gas particle or that gas particle. It's just irrelevant. So all that matters is how many moles you have. And this is actually leads us to Dalton's law of partial pressures, which he simply says, hey, the total pressure, find out the pressure of every individual gas, add them all up, and that's the total pressure inside the container. So we knew the blue particles were doing half this value, and then when we add the red particles, you get the other half. So it's doubled, about 11.5 each maybe. And so that's Dalton's law of partial pressure. But the other thing I think that's obvious and we're seeing now is the fact the red particles are really flying around a lot faster than the blue particles. Now, how could we have predicted that in advance? And this is what Einstein did. He did a lot of what we call theoretical physics is his particular one, but there's theoretical chemistry as well. And if you look at the kinetic energy formula, it's 1/2 mv squared. And since the gas particle, the red one, is smaller, m goes down, that tells us that the velocity has to be higher. It's going to be moving faster because they're going to hit the wall with the same momentum, the same kinetic energy as each other. And if it's smaller, it needs to be going faster for that to happen. Now, what Einstein did was he would just sit down with a piece of paper and do math and formulas. And from that, he would come up with scientific discoveries. And in fact, I know of one of his discoveries that his hypothesis wasn't experimentally proved until 20 years later, when there was a solar eclipse that finally gave them the ability, astronomers, the ability to watch and see light bend around a planet, and that proved that light was both a particle and a wave. He had predicted that from mathematics, from theoretical physics 20 years earlier, and it only, we had to wait until there was a solar eclipse before we experimentally test it. And this is really, this theoretical chemistry, theoretical physics, all of this mathematical, computational, has opened up science exponentially. I mean, we're doing things theoretically and based off of mathematics far beyond what we could have done just 150 years ago. And so you're seeing a glimpse here into the power of mathematics applied to science, and how mathematics can simply explain the behavior of the environment around us and make things pretty simple.